In this video, we'll be solving CS2 paper B for IAI July 2022 term. We'll cover the solutions, indicative solutions of these. There might be differences in the codes from what you have written, but this is the best possible estimate of the solutions. So, starting from question 1, this is the PDF of a GEV distribution is already given to us, where CDF is this and PDF is this. And based on historical data, the maxima value for 3 years of the data, 8, 8, 9, is also given to you. Write a function in R to compute the log likelihood of the above distribution. So first we'll input the data into R, which is data of C8, 8, 9. Then we have the log likelihood function, which is a function of parameters, and the complete distribution from here is put into here. And then this is log of f minus the ln f is log of this entire f, and since in R we need to take a negative log likelihood, that is why we take a sum of minus of log of f and we run this function. So first data, then FMLE, and then if you run, then in the next part, they've said use a function in part 1 to find the MLE of the 3 parameters alpha, beta, and gamma. You can use alpha equals to 6, beta equals to 4, and gamma equals to 5 as initial estimates. So they have been given 6, 4, 5 as initial estimates. We can store MLE using NLM of FMLE, comma P, and then we can get the values of alpha, beta, and gamma using MLE dollar estimate of 1, MLE dollar estimate 2, and MLE dollar estimate of 3. Then we need to see that using the MLE parameters, we need to estimate the probability that any claim, that a claim in any given year is greater than X. So we create X, which is a sequence of 10 to 100 divided by 5. So probability P will be nothing but 1 minus EXP of minus 1 plus gamma. Again, this is given in the question for CDF calculation. So just directly inputting that. And if you calculate P, you get the probabilities. Next part they have said is plot a curve of the probabilities against the maximum claim in a year and do appropriate labeling. So plot X comma P, X lab is maximum claim in a year, Y lab is probability, and mean is X versus P, type is equals to L, because they've sold to plot a curve. So curve means a line. So we have to write type equals to, this is the graph we get. Then we write, explain the reason associated with the shape of the curve generated in part 4. So this is an exponential type of curve. So GEV distribution already also has an exponential type of parameter and it's in it. So therefore, the exponential parameter will cause the curve, the shape of the curve to be this. Also, as X increases, as probability increase, as X increases, the probability of claim in maximum claim in a year also decreases. Moving on to question 2, you have been asked to analyze the number of deaths per month in the country X from lung disease over the period January 2015 to December 2020. This information is contained in a time series called lung.csv. Convert the data into time series format representing the above period after loading it into R. So we do a set WD, we set the directory. Then we import the data in the time series format, that is TS of read. This is importing the data, then start should be January 2015 and frequency is monthly given in the question. You can check the data, start of data is 15/1 and end of data is December 2020. So this can be already found out from our plot. Then we have plot this time series giving appropriate label for each axis to ts.plot of data. So when we plot, the time series look like this. It's an additive time series. When we plot on 2 separate graphs, the sample correlation function and sample partial autocorrelation function of the series with appropriate labeling of the axis. So ACF of data and PACF of data, and you can label the axis accordingly, whatever you get. Then justify the presence of seasonality in the data based on 2 and 3 above. So from 2 and 3 above means plot the time series. So from the time series, we already saw that there is seasonality in the data. If you zoom the data more, you will see that the seasonality is yearly on a yearly basis. And similarly, from the ACF also, we see that the seasonality is on a yearly basis. Then apply the seasonal differencing in the time series to remove the element of seasonality. So we'll see the difference in data is the diff of data lag is equals to 12 since it's a yearly seasonality and difference is equals to 1. Then we have been told plot the ACF and PACF of this time series generated in part 5 up to lag k equals to 5 giving appropriate labels. So first we need to understand plot the ACF, which is lag dot max is equals to 60. Why have I written 60? Because it said lag dot max k is equals to 5 years. Our data's frequency is 12. So 12 into 5, 60. So we can see that there's no seasonality now in the data. And PACF also shows no seasonality. Then comment on your plots in part 6 making reference to stationarity. So data was initially stationary also 0.02 which is less than 0.05. So we have suction evidence to reject now. The data was stationary previously and after differencing also it is stationary. The data had only seasonal difference, seasonality in the data. Next question 3, the number of customers arriving to a grocery store can be modeled by a Poisson process with a rate of 30 customers per hour. Find the probability that there are 2 customers between 10 a.m. and 10:15 a.m. So lambda is 30 by 60. Then we have depoys of 2 comma lambda into 15. Why lambda into 15? Because first we found out the lambda per minute and then lambda into 15 will be per minute parameter lambda t and depoys of 2 because 2 customers. Then find the probability that 7 customers between 11 a.m. and 11:20 a.m. So 7 comma lambda into 20 and then 15 customers between 11:20 and 12 noon. So lambda into 40 because 40 minutes. Prepare a probability distribution table for different number of customers at any given 10-minute interval. So x is 0 to 20, p is depoys of x comma lambda into 10 and data frame of x into x comma p. This is very direct. Next is refer to data1.csv. So we need to import the data1.csv. Then write down the formula for estimated integrated hazard and its estimated variance using the Nelson-Adel model. So this can be found in the tables. Lambda j is equal to dj by nj and estimated integrated hazard. And estimated variances also can be found in the table, that is dj into nj minus dj by nj cube. Okay, so data, then we'll find load the data into R, add new 2 columns to the table and populate the estimated integrated hazard and the estimated variance. So, integrated hazard is data $lambda j. First lambda j is dj by nj and integrated hazard is cumulative sum of the data $lambda j. Then we have the variance. Variance is nj minus dj by data $nj whole cube. Then we have produce a scatter plot showing the values of the estimated integrated hazard across Tj for j equals to 0 to 20 together with the 90% confidence interval values. So we'll first find the standard error. Standard error is cumulative sum of variance. Z is Q norm of 0.95 since 90% confidence interval, two-sided test. So we'll take 5% on each side. And Nelson-Allen model confidence interval, we'll find out Tj is equals to data $Tj, then lower value will be minus of Z into lambda j into SC, and upper will be lambda j plus Z into lambda j into standard error. This gives us the table for lower confidence intervals and upper confidence intervals. We need to make sure that the lower confidence interval starts from 0, and then we'll plot the first sensor scatter plot. So time, it has to be time and lambda j, then lines of confidence interval on both sides. Okay, then we have question 5, which says write a general function to compute the truncated moments of a log normal distribution. So this can be found in the page 18 of the table. It's a function. You can see the function and input them. So function of k sigma mu lu e to the power k into mu plus 0.5 k square into sigma square into PL norm log of u minus mu by sigma minus k into sigma minus PL norm of log of L minus mu. By sigma minus k into sigma. So this is the function we create. Then they've told us, so just creating this function is 4 marks. You have to just input the function. Then they've told us the values of sigma, mu, L and u. So sigma, mu, L and u. And then we have been told use a function generated in part 1 to compute the first and second order truncated moments, means k is equals to 1 and k is equals to 2. So in the order we input the variables, just put the values of k1 and k2, we got 2.34 and 28.17. Then they have told us use the function one or otherwise compute the first two truncated non-truncated moments of a normal distribution. Normal distribution with mu and sigma will just be values of mu and sigma, that is 1.2 and 0.7. But I think this is a printing error mostly. It should be log normal distribution because above one is a log normal distribution. We need to compare the results in the next part. So for log normal distribution, the values are e to the power mu plus 0.5 sigma square and e to the power 2 into mu plus 0.5 into 2 into sigma whole square. This can be again found in the table to see the values. So M1 is 4.24 and M2 is 29.37. We see a significant difference in the mean, but variance does not differ by much. Then question 6 is refer to the data set cricket.csv. The data contains the following columns. Name of the player, all these columns are there. You can import the data. So read.csv, we can see the columns here. Head of cricket. Head of cricket. So this is there. Then we need to find out what is the average of runs and wickets for the three groups of players based on initial groupings. So we need to find the average of runs and wickets. We'll find the aggregate function will give us the sum of the number of, based on each of the group, what is the sum of the runs. Then we can find out the count of the number of people of the runs in the initial group, which is 42, 74 and 72. And then you can find out the mean. Mean will be these values. Similarly, for wickets also we can do the same thing and we will get the value. Then they've been told us to create a copy of cricket and rename it as cricket 1, and cricket 1 keep only the 4 numerical columns and remove the rest of them. Cricket 1 is equal to cricket of 4:7. That is only the 4 numerical columns, last one. And then they've told us run the following feature. This code they've given and just need to run this. Then they have asked us to say create a seed value using the following code of set.seed of 100. So this was created. Then we have been asked to execute k-means clustering on cricket 1 and assign it to the variable cluster cricket. Print the cluster means of the generated clusters. So cluster cricket will do this. Then we need to print the cluster means of the generated cluster. So cluster cricket $. So this gives us the cluster means. Okay. Then we've been told us add the cluster memberships of each of the players to the original data frame by creating a new member class membership. So cricket $class membership, and I stored the cluster inside this. Then we have renamed the memberships as batsman bowler by the following rules. Cluster with the highest average runs is named as batsman. So this is run and a highest average is for cluster 2. So cluster 2 will be renamed as batsman. Then next one was said as with highest number of wickets, it's bowler. So wickets cluster 1 is bowler. And all others are all-rounder. Okay. Once you do this, then you've been said compute the error rate in clustering by comparing initial grouping with the clusters created. So we'll take out the count of the initial groupings and we'll take out the count of the new groupings, and then we'll find out the error rate, which is D1 minus R1 by D1. So 16% error rate, D2 minus R2 by D2 is 45% error rate, and D3 minus R3 is completely error, 100%, 107% error rate in negative. And they ask comment on the possible reasons of classification. The reasons may be because only wickets and only runs have been considered. We did not consider on any other. The last four variables were actually, we did not consider the average batting average. We did not consider the number of runs. We just, and wickets, we just did and we did not consider the economy also. We just did a based on the average number of runs and wickets we calculated, which is completely wrong. We cannot do on these bases. So that is why there can be misclassification in the data. The paper was quite direct in terms of how the sums are, like everything is from the syllabus, and you can be referring the tables to get your answers directly. So yeah, the paper was good.